Hey everybody, I'm sorry, I don't know why it disconnected. Sam, you needed a password, was that correct? Okay, I'm gonna send it to you privately on the chat. If you guys want to take a minute, go ahead and do your attendance. And then Lynette, you needed one as well? Okay, I'll send it to you in a private chat. And same for you, Marcus, I'll send it to you. It's a very informative book though, Haley. It's a good book.
I got through the first chapter of it, and it's really interesting how it actually started out from the very beginning. It's kind of cool.
Yeah, it gives you some history. So it is thicker than some of the other books because of that. But it's not very difficult. I don't think it's too technical.
And I enjoy reading, so it kind of gives me an excuse to check out from my family.
Does anyone else need their college technology computer passwords?
When did they change again this semester?
I have no idea. Gail just sent me a list and said if students don't have access, this is their passwords.
Well, I was able to log on yesterday. So.
And you're not on my list.
Oh, well, good.
So probably because you could log on. And Lynette, you're actually not on the list either. So I'm gonna send Gail an email and let her know that. And I'll CC you and she can get you your password.
Do you have the list?
I do. Okay. That takes care of that. One last reminder, make sure you guys do your attendance. Does anyone need me to enter it for them? Did everyone get it? Okay. So let's jump in to talking about fission and a little bit about fuel. Some of the fuel information should be a review from materials. But we're going to start talking about neutron interactions and mass defect. You guys see that okay? Or do you need the lights off in front? Okay.
Yeah, I don't know. Is that okay?
If you guys are okay with that, you still take notes?
Mm-hmm.
Okay. And let me share the screen for everybody online. Okay. Can everyone online see that presentation?
Yeah, we see it.
Okay, great. So we're going to start today. We're going to talk about the mechanism of these different types of neutron interactions. From the materials class, what kind of materials scatter neutrons?
Graphite?
Graphite, reflectors, and one other general type. What? It does scatter. That's a specific element that does. So heavy water, deuterium, graphite, they're all scattering materials. What role do they serve? We heard reflector, moderator. So reflectors and moderators scatter. What about absorption? What absorbs neutrons in the reactor?
Poisons.
Poisons, control rods. Exactly. We also have capture, which we didn't talk about in the materials class. We're going to talk about this a lot when we get to our discussion of K effective and the neutron fuel cycle. Because what's going to happen is material like our fuel first captures a neutron. Our fuel is then going to fission. Some of our non-fuel items or some of the atoms in our fuel that just statistically are not going to fission will still capture that neutron. They're still going to take it out of the equation, but they're not going to produce a fission for us. So we're going to learn about capture and fission together because that happens in a material that's often capable of fission, but not every single time a neutron hits a fissile material does it actually fission. So this is what happens when it doesn't fission. But we're going to go through the mechanisms of how these reactions are occurring. And then we're going to talk about energy from fission and how we get these neutron interactions and how they release energy and how we split energy. And then we're going to talk just a little bit, is fissile versus fissionable. That should be a review, but just want to make sure those terms are fresh in our minds for the rest of this semester too. Okay, so we reviewed yesterday, neutrons have no charge, right? So they don't interact with the atomic electrons. When you guys were in chemistry, your valence shells and your electrons moving back and forth and your metallic or ionic bonds where those electrons are shared, that was a huge driver for most of the reactions you studied in chemistry, right? I would say the vast majority. In nuclear physics and reactor theory, which is what we're studying right now, we're pretty much not going to talk about electrons. Nuclear engineers, nuclear operators, nuclear physicists, we just don't care that much about electrons until we start getting to the energy production, right? In our turbines and our generators and some of our components that are electrical. What happens in the reactor is all going to be collisions of the neutron with the nucleus of the atoms around it. So that's what we're going to focus on, okay? So neutrons have energy, okay? And the types of reactions and the probability that a certain reaction will occur depends on the kinetic energy of that neutron. Do you guys remember from thermo what kinetic energy is?
It's the energy of motion, isn't it?
Energy of motion. So when our atoms are moving around, when our ball was rolling around the track, we have kinetic energy, right? There is not an agreement among scientists, engineers in different fields about the actual exact classification of neutron energy. When we're looking inside a reactor, there is actually some amount of the physics going on that we do not understand and cannot model precisely mathematically. It is in the realm of modern physics, where everything is a probability distribution. We think that these things are going to happen, and we've observed that they're going to happen, but we don't exactly know when and how often, and we can't predict it. So one of the things that is really, in my mind, so incredible about reactors is they were built, starting 60, 70 years ago, where they hadn't even been able to see and create rough models. And so they did all this approximation and they were right. They built something that worked and honestly pretty safely. Like, we're going to talk in capstone about some of the pretty major accidents, but compared to, for example, coal, which everyone considers pretty acceptable, nuclear energy has killed a fraction of the number of people in our energy production than coal has. But when we're talking about the nuclear reactor, this breakup of energies is pretty well accepted. Sometimes physicists who study neutron energy for different reasons than just necessarily building a reactor will want to break it up differently. But for the purposes of this class and for the purposes of your careers, thermal neutrons are below 0.025 electron volts. Slow is anything below 10 electron volts. Intermediate is from 10 to 100. We don't really interact with this very much. We tend to really just look at slow and fast, and we kind of group intermediate with fast, okay? Fast is going to be greater than 100 kiloelectron volts. When we're talking about fast and slow neutrons, all of the commercial power reactors in the United States want to operate with slow neutrons and thermal. We don't typically see fast neutron reactors except for experimental reactors. And we never use prompt, which is the opposite of thermal. So there's slow and fast, and then there's thermal and prompt, and I don't have prompt on here because we don't use it. Prompt neutrons are only used in pulsing. So the treat reactor, which is capable of pulsing, it will allow that pulse to use prompt neutrons for a fraction of a second before it auto shuts down. And then because it was prompt neutrons, it then takes several seconds for the reaction to actually slow down. And so that's why it's only used for pulsing. Okay. So depending on that energy that the neutron is, these are the types of interactions we can have. Scattering and absorption. So if I were you, and I'm trying to keep this straight in your notes, I would make a tree. We've got neutron interactions at the top. They can break down and they can either scatter or they can have an absorption reaction. Under scattering, split that again, another tree, we can have elastic or inelastic, which we will describe and define in just a moment. Over on the absorption side, our absorption reactions can split into radiative capture, particle ejection, or fission. So now essentially you have a cascade of what that neutron can do, and it's classified under scattering or absorption. So that's how I would think of it. All neutrons are born fast. So whatever occurs in the nucleus, where you have now a neutron by itself, it is always fast. In fission, we're actually going to produce neutrons at two different times. The first time they're born, they're prompt and fast. The second time they're born, they are delayed and fast. Okay? Once they are in our material, we're going to slow them down by scattering. So we're going to purposely have moderators and reflectors that undergo these types of reactions so that we can moderate our neutrons so that they are slow. And specifically, we want to get to thermal, that very slow speed, right? Finally, in our reactor. They're going to undergo an absorption reaction in our target nucleus, so in our fuel. And then all of these are possible. You guys remember on the chart of nuclides where we would look up our fission cross sections? Okay, you remember at the bottom how there was also a sigma A? So the sigma F is the probability that of all these reactions, we're going to get fission. The sigma A is the probability of these other absorption reactions. Good fuel has a very high fission cross section and a lower absorption cross section. Because every time one of these things happens to our neutron, it has been parasitically absorbed. It's been taken, absorbed, and not created more neutrons and not created energy. So we want to tilt our reactor so that this is the most likely thing to occur in the fuel. Okay. Scattering reaction. When a nucleus is struck by a neutron and then subsequently emits a single neutron. So if you think of a pool table and you've just racked all of the billiard balls, right? They're in that little triangle when you start your game. That's your nucleus. You're going to take your cue ball and it's going to hit and it's going to bounce somewhere else, right? That's a scattering reaction. If you do a good job, you're going to knock the billiard balls around, right? And so maybe your cue ball gets stuck in the middle and a different ball is what rolls away. That's a type of scattering too. But billiard balls are a really good analogy for scattering reactions, okay? The initial neutron that hits the nucleus and the final neutron that is emitted are not necessarily the same, right? So that cue ball might get stuck in the middle of our nucleus and a different billiard ball comes out, right? We have scattering and elastic and inelastic scattering, okay? In elastic scattering, there is no energy transferred into nuclear excitation. So in our billiard balls analogy, right? The cue ball does not go into the middle of the rack balls, sit there with stored energy, and then knock everything away, right? It comes in and it bounces off. Elastic scattering does not have an excited state. It's just a bounce. Momentum and kinetic energy of the system are conserved. So even though some of that energy is going to go into the nucleus because the neutron hit it, when that neutron is emitted, it's going to have that same amount of energy. It's going to conserve it overall. This is the most common type of neutron interaction. If you are not sure what is occurring, you know, I ask you a test question, what kind of reaction is this? This is the most common type. Pretty much everything will scatter. We have to look for very specific things that fission, right? In inelastic scattering, the incident neutron is absorbed by the target nucleus. We're going to form a compound nucleus. So instead of the cue ball that hits the rack and knocks everything around, this time our neutron is going to actually become part of the nucleus in the mix of protons and neutrons that were in that atom, and it's going to create an excited atom. So the energy that the neutron brings is now part of the atom. It's created really a new isotope, right? But because nature abhors being excited, in nature, everything is driving towards being its lowest energy state. That compound nucleus does not like this addition of energy and mass. And so it's going to kick out a neutron, and it will have lower kinetic energy than the one that entered because some of that energy was just absorbed in becoming an excited state. And so to get rid of all the energy it absorbed and go back to its ground state, it's usually also going to emit a gamma. So inelastic scattering is now going to have radioactive properties as well. Right? So we excite our neutron, we absorb that neutron, which makes a new isotope. Now that isotope is unstable, energetic, and in need of decay. So it's going to emit a neutron, may or may not be the one that hit it, doesn't matter, and a gamma. And that will return it to its ground state.
Doesn't emit any particles as well?
The neutron,
Just,
the neutron is the particle.
I mean, once it hits and it's absorbed, and then that gamma ray is emitted, are any particles also?
So typically, the neutron is emitted first, but because it spent some time absorbed in that nucleus and giving excitation energy to the atom, the neutron it kicks out is lower energy than the one that came in. So that nucleus still needs to release some energy. So then it releases energy in the form of a gamma. So the particle that comes off is a neutron. Then there's still some energy, so there's also a gamma. Okay, any questions on scattering reactions? All right. Jack, were you speaking, or is it just highlighting your box for no
I'm just
reason?
highlighted, I guess. Actually, it might have known I had a thought. Can I ask you a question?
Yeah, go for it.
So with elastic scattering, does that mean that the atom that was struck, does that go back to being completely unchanged?
Yes.
And
So
with
just,
elastic, since it ditches a gamma or two, it would actually turn into a different something else, right?
no, it goes back to being its original nucleus. It becomes a different isotope of the material for some amount of time as it absorbs that neutron. But then when the neutron leaves, it goes back to being that same element. And then when the gamma leaves, it goes back to being that same element at the same energy that it was.
Okay, cool, thanks.
Would you say what a prompt neutron is again?
A prompt neutron is the first neutron that's born after fission. Any other questions?
That was a good question, yes.
Okay, there's no more questions. We're going to move on to absorption reactions. Okay? Absorption reactions are going to result in the loss of a neutron coupled with the production of a charged particle or gamma ray. So what's going to happen is that neutron is going to go into that nucleus, but we're not going to release just a neutron. We're going to release some charged particle and or gamma ray, either through radiative capture, particle ejection, or fission. And in fission, we do release neutrons, but in addition to some other things. Okay?
I have a question.
Yeah, go for it.
When you say that the charged particle or it's gonna the particle ejection, what is that particle? Like, what is it?
We are going to talk about that. It can depend based on the energy and the target nucleus. But we'll start defining those in just the next slide, actually. When the target nucleus is radioactive, and then you absorb a neutron, in addition to our charged particle and gamma, we're also going to emit some additional radiation. So when fuel, like uranium-235, which is radioactive, absorbs a neutron and undergoes fission, we're going to release some beta and gamma irradiation as well. So that's why our nuclear process is radioactive. We're using an already radioactive material, we're giving it more energy, we're producing more radioactivity. Okay, now to start answering Haley's question. Particle ejection. The most common particle that's ejected is an alpha particle. Alpha decay is the classic example of what particle ejection is. There are sometimes you might see some betas ejected. You might see some different neutrons come off as the particle. But by and large, when we talk about particle ejection, we're going to see an alpha. Okay? So what happens is we have our target nucleus and our neutron is going to hit it and be absorbed into it. Okay? The newly formed compound nucleus, so this isotope we've created now, has been excited to a very high level of energy. And so instead of just spitting the neutron out again like we did when we scattered, it's going to eject a whole new particle. In particle ejection, the incident neutron remains in the nucleus. So we talked about inelastic scattering. We can eject the same or a different neutron. In particle ejection, we're never ejecting the same neutron. It's a whole new piece that comes out of this atom, okay? After that new particle is ejected, the remaining nucleus may or may not exist in an excited state. So do you remember in materials when we looked at the chart of nuclides and we followed a decay chain? And sometimes there were multiple alpha emitters in that decay chain. So you might emit your particle and that neutron might still have too much energy. So it needs to emit another one and another one, right? So it's not necessarily like elastic scattering where we remove one neutron and we remove a gamma and we're back to our ground state. You might have a lot of excited energy of excitement that was absorbed through that one neutron, and it might kick off a lot of particles. This is a highly energetic reaction because if you think about it, we discussed this and we did a little reminder yesterday, but what is an alpha particle? Yeah. Or sorry, you said helium is hydrogen. 4-2, hydrogen, right? It has 2 neutrons and 2 protons in the middle of it. It is a full atom. So when something alpha decays, this is a huge particle. It is forming a whole new atom and kicking it out. That takes a lot of energy, which is why alphas can be so concerning as a type of radiation, because even though they're huge and they can't travel through very much, right? Our piece of paper can block them. They have so much energy, they exist for such a long time. If, as we discussed, you inhale it and it's bouncing around inside your lungs because it can't escape, it's going to be depositing a tremendous amount of energy for years. So even a little bit of inhalation can cause a large dose. And the reason that that's true of alpha is that we're forming a highly excited compound nucleus, and that's what leads to ejecting an alpha particle. Does that make sense? What's happening there? Mechanism? Okay. Does that answer your question, Haley?
Yes, thank you.
It keeps decaying, keeps different isotopes stable.
Yes.
Decay, stable, just depends.
And how much energy and what kind of decay will determine how long it spends decaying. Okay. Radiative capture. A neutron is going to enter the target nucleus, and we're going to form a compound nucleus again. Okay, we have some isotope. But instead of ejecting a particle, we don't have enough energy in this new isotope. So we're going to decay by gamma emission. Radiative capture decays by gamma. Absorbs that neutron, and it gives you multiple gammas instead. This is actually the most common type of reaction to occur when we're talking about thermal neutrons. So scattering reactions are the most common to occur with neutrons at all. But when you have thermal neutrons, they're a little bit more likely to undergo absorption, specifically radiative capture. So when we lose neutrons and they're absorbed and they don't create a fission, they are instead creating gammas. One of the things you will notice as operators is when you have your reactor on, for lack of a better term, and fission is happening, you get a tremendous gamma dose from the core. And when you shut that reactor down and it's no longer fissioning, your gamma decays away right away. Because you're continuously producing gammas from all the neutrons that don't fission but are absorbed and have radiative capture. We produce a little alpha too because we have particle ejection happening. And that can be an issue because it can activate our water, we talked about. But gammas come from this reaction happening in the reactor. Okay. Then last of our absorption reactions, we have fission. The one that is of most interest to us, the one we want to have occur, right? The nucleus is going to absorb the neutron, and then it's going to have so much energy that it needs to release that it's actually going to split in half and create two new atoms. And whatever neutrons don't end up in the nucleus of fission product 1 or fission product 2 are going to get spit out as neutrons. So this one we're going to visualize, right? Our neutron hits our target fuel atom. We're going to call this U-235. It does have to be heavy and unstable. So U-235 is already radioactive, right? That's a signal that it's an unstable nucleus. And it's heavy. We're not going to fission helium or lithium that have 4 and 6 and 8 for their atomic numbers, right? We're going to fission things that have 235 as their atomic numbers, 238, 239. That neutron, when it's absorbed, this atom becomes excited. And it's going to split into a fission product and a fission product. It's going to create a neutron or two. Then these fission products, they're still excited. And they're going to eject a neutron or two. The ones that come out immediately are our prompt neutrons. The ones that come from the decay of the fission products are our delayed neutrons. We want the delayed neutrons to scatter, become thermal, and go on to create more fission. We want the prompt neutrons to absorb and not fission. We don't want them to be part of our cycle because they will make the reaction move on such a fast time scale that we cannot hope to control it. So we want to focus on these delayed neutrons that come from the decay of the fission product fragment. Any questions on that? Okay. When these neutrons leave our fission products, they're going to go hit more 235 atoms, which is going to create more fission, right? If we produce enough neutrons to hit enough fuel atoms to continue this cycle without us needing to feed it more fuel or neutrons, we can create a self-sustaining chain reaction as long as we have fuel in the reactor. That self-sustaining chain reaction is when we have criticality, right? So if it continues without fissioning more or less, just continues, we're critical. Supercritical is then we start having more neutrons and we start creating more interactions and we go up in power, right? We're producing more and more heat, which is more and more power in the core. We're gonna watch a little video that I like to just visualize a chain reaction. Maybe if it'll play. Can you guys see this online?
Yes.
Yep.
So there's our visualization of a chain reaction. There's also another one on here, ping pong ball mouse traps. You guys are welcome to watch that video. We also have a ping pong ball reactor that the class above you guys built. I didn't experiment with it with the 151 students, and it just takes a really long time to set up, so I'm not doing a demonstration today. But if you think about our matchstick chain reaction, did all of the matches light? Eventually. It's kind of hard to see very clearly, but I think all of them did. Do all of the ping pong balls fission when we set off mousetraps? Have you guys seen one of these before?
No.
Mousetrap reactor? Okay. Let's look at the video real quick then.
You like Bon Jovi?
Do I like Bon Jovi?
Yes, I know. I noticed that too.
Oh.
Right.
No, I don't know why he's on that list.
I would not want to be.
So does it look like any didn't go off? Looks like they pretty much caught it. Okay, so in that scenario, it's actually a really excellent way to think about a nuclear reactor. Your mousetrap with a ping pong ball is an atom of U-235. That initial ping pong ball you drop in is your initial neutron. And as it hits each nucleus, it's going to eject more neutrons and have fission fragments left behind. Did all of the ping pong balls fission in that? It looked to me like they did. Then all the matches light. Joe thinks so. I think so. Is uranium-235 the same?
No.
No. So this is the weakness of our analogy, right? U-235, the ping pong ball can only undergo the one reaction, right? The match can only undergo the one reaction. Uranium-235 has 3 different types of absorption that can occur. Fission, radiative capture, and particle ejection. So sometimes our uranium-235 atoms are not going to fission. Sometimes in our reactor, the neutrons don't even hit uranium. They spend their entire life scattering around in our moderator and they never make it to the fuel. They're an unproductive member of our neutron family. When we have fewer fissions happening, the chain reaction will slow down and stop. We do that on purpose when we put control rods in that will absorb and not fission, right? Poison control rods have radiative capture and particle ejection happening, but they're a material that has no probability for fission occurring. So they take all these neutrons and they create gamma or alpha, but they don't create any fission and they don't create any more neutrons. Okay. One of the reasons that fission does not always occur is there is a minimum amount of energy that atom has to hit when it absorbs the neutron, that minimum excitation energy, for it to break apart and release heat and neutrons. This is called our critical energy. For fission to occur, that excitation energy when it absorbs a neutron must be above some particular value that is specific to that nuclide, right? So uranium-235 is going to have a different critical energy than uranium-238. Okay, we're going to switch gears a little bit. So we've talked about those interactions. Now we're going to talk about how we can even get energy out of the breaking apart of an atom. Mass defect is not necessarily specific to fission, but we're only really going to calculate fission, okay? Mass defect is the difference between the mass of the atom and the sum of the masses of its parts. Do you guys have your charting nuclides books with you? Okay, you guys can borrow one off the shelf if you don't have yours. Those of you guys who are at home, take a second, pull out your charted nuclides book. Let's take a look at uranium-235. What's its atomic mass? Not quite. Close. Very close to 235.
$235?
Uranium-235, what's the atomic mass?
Is it this bottom number? 235.043930?
Yes, that's correct. You see that, Patel?
I'm not quite there yet. I'm writing you.
Okay.
Where was 235?
Uranium-235.
Okay, and then what did you, I'm sorry, I didn't hear you.
That's okay.
235.
What is the mass? What's the atomic mass number?
Yep. 235.043930.
Yes. The mass of a neutron, if you guys turn to the back of the book, there's some constants listed. It'll have the mass of your neutron. So, slightly less than the sum. So the mass of the atom here, right, is 235.04. When you do these calculations, you usually have to go out to at least 4 significant digits because we're talking about such small numbers. So I'm going to go out is 6 there. The sum of the masses, okay. In uranium-235, how many protons are there? Okay, 92. And what's the mass of a proton?
1.00727.
And for our mass defect, we're gonna also add in our little tiny mass of electrons here, which is 0.000548. So that's our protons and electrons. How many neutrons are there in uranium-235? Can someone online tell me how many neutrons?
143.
Yes. So does everyone see 235 minus 92, 143? What's your question, Joe?
Were you getting the masses for the protons and the neutrons here now?
In the back of your book, there's a,
Like on the last page?
no, there's a whole little
All
appendix
right.
in the back that has constant.
I mean, it's in the DOE manual.
It's right, yeah, on page 92.
So, right here. Neutron mass, proton mass. And we're looking at the version that has AMU as the unit. Okay, so what's our mass of a neutron?
One point zero zero 86665.
Right. So, if you take 92 times the mass of your protons plus the mass of your electrons plus the number of neutrons times the mass of the neutron minus the mass of the atom, what do you get left over? I know you guys online probably can't see, so we've got our mass of our neutrons on the back page of our chart of nuclides, which is, and then we have 143 neutrons, and you're going to add that to 92 times the mass of our protons plus the mass of our electrons. And then you're going to subtract the total mass of uranium-235. What do you get? You have a calculator with
I
you
don't
now?
think I did it right, but
Okay.
I got 1.8652036.
Close to what
Wasn't
I got.
necessarily following you.
Okay. That's very close to what I got. I got 1.91517. Okay.
that 3 zeros where you wrote to the furthest right?
Yes,
Is it-
0.000. This difference, which is in atomic mass units, is our mass defect. So there's a disconnect between what we measure the mass of the whole atom to be and what the mass of each part is. This defect is what we can convert to energy when we split apart this atom. So this defect, because mass and energy are equivalent, right? Einstein in his famous E equals mc squared. Essentially what he was saying is that energy and mass are the same. We can convert between them. So this little tiny bit of extra mass that exists in every atom, this is what we convert to energy when we fission. To go from this mass to energy, we're just going to multiply by c squared. We're going to convert it to energy, which is a constant, which we'll do in just a second. Anyone else online get an answer for that mass defect?
Got 1.6846.
Okay.
But I might have screwed up. Were you supposed to add the first two numbers you put in there?
Yes, so you're gonna multiply 143 times 1008665.
Okay, my bad. I added those and then added them to the next part, and then so yeah, I did it wrong.
All right, so this is the answer I got, 1.91517. And I'm gonna pull up an actual calculation from the DOE handbook. I just kind of wanted us to walk through that. This will help anybody who's confused. So this equation right in the middle of the page, that's what we just did. Right? So if we're talking about uranium-235, what's the mass of our atom? This is what you looked up on the square for U-235 in your chart of nuclides. 235.04394. So those of you online, what's the mass of a U-235 atom?
It's 235.04.
Yes, and make sure you're using at least 4 significant digits. So at least 235.0439. And we're dealing with very, very small amounts of mass. So you have to be very, very precise or else you won't get an answer except 0. Okay, what is our Z number?
92.
Correct. What is the mass of a proton? In the very back page of your chart of nuclides. Rest mass of a proton. It also happens to be on this handbook page.
1.0072.
Correct. And the mass of an electron.
.0005.
Yes. And for that one, I keep going. They're so small. 5486. What is our number of neutrons? Our A number minus our Z number?
43, wasn't it?
143, exactly. And then the mass of a neutron? 1.008. Put those numbers in. That's how we calculate our mass defect. You have a question, Joe?
Probably. So my number was pretty close to yours,
Yes.
but it wasn't the same. That's basically not right. It's not close enough, is it? Because of the tiny numbers.
Exactly.
So-
You probably rounded something somewhere.
I didn't, well, I just might have made a mistake too, but so if you use 4 digits and I use 6, we're gonna get different answers? And then-
Slightly.
And that's not gonna be acceptable, or will that be acceptable at that point? Because I just,
So after 4 significant digits, so I got, 1.915, you got 1.8 something, right? So because that first decimal is different, they're two different. But if I got 1.915 and you got 1.912, now we're close enough because we're out at that 4th digit. We've run over time a little bit. We're going to go over this again next lecture, and you guys are going to do calculations on Thursday. So if you're a little confused right now, don't worry. We'll do this some more. But I know I've run over. I have to get to another class, and some of you do as well.
your office hours are at when today?
My office hours today are after the 153 lab, which should be 11. Let me just make sure. Sorry, my office hours today are from 1 to 3. I've
Can
got
I ask
radiation.
you a question?
Yeah,
Have you heard from INL about their job postings yet?
I have not. I do know that the INL is going to come recruit for internships on the 21st, I think, of this month. So they're planning to come and they want to hire ESTech students, but I haven't heard about the jobs. They're just talking about internships right now. All right, guys, I gotta get to my other class. I will talk to you guys again tomorrow.
Is that in here?
No, it's not in here.